And chapter 12, of course, is all about Earth, Moon, Sun. Basically, the basic parts of our solar system having to do with just the Earth, the Moon, the Sun, the tides, different seasons, laws of gravity, weight, inertia, and phases of the Moon. The rotation is something that happens around an axis. And an axis is a straight line that goes from the North Pole to the South Pole. The axis, or the rotation of the Earth around its axis, takes what we call one day. And that's 24 hours. And the axis of our Earth is tilted about 23.5 degrees. And because of this rotation of the Earth and the tilt of the axis, it results in day and night. It means that we have 2 high tides and 2 low tides every day. And those high tides and low tides fluctuate, meaning that some are really high, some are really low, depending on where the Earth is in its orbit around the Sun. And it also creates ocean circulation, which is super important for climate, which is the overall weather of the entire Earth. Revolution or orbit, on the other hand, is something a little different. The orbit, or the revolution of the Earth around the Sun, takes what we call 1 year, about 365 days. And that results in seasons and climate and even weather sometimes. So the difference between weather and climate is that weather is local and temporary. Climate is global and over longer periods. And the orbit and revolution also contribute to ocean circulation patterns. And changes in that orbit over time are very slow, but it does occur. And I think I mentioned last time about the Milankovitch cycles every 26 million years, and the flipping of the Earth's magnetic and north and south poles. So the seasons are created by this orbit of the Earth around the Sun. So let's start with the summer solstice. That is the longest day in the north, and the north end of the Earth's axis is tilted towards the Sun. That's why it's the longest day. And it is summer in the northern hemisphere. However, in the southern hemisphere, it's winter. Going to the September equinox down there in the bottom in the middle, the March and September equinoxes, neither end of the Earth's axis is tilted towards the Sun. And both hemispheres receive the same exact amount of energy. So day and night are equal. The amount of time of day is equal to the amount of time of night. The winter solstice, all the way on the right, happens December 21st, and it's the longest night in the northern hemisphere and the shortest day in the southern hemisphere. The south end of the Earth's axis is tilted towards the Sun, and it's summer in the south. So December 21st is the middle of summer in Australia, and winter in our area. And then finally up there at the top, the March equinox, day is again equal to night. Okay? And that's what we just passed through. Top, middle is where we just last week, in fact, passed through our March equinox, where day and night are equal. And we are now heading into the days being longer and longer and longer in the June solstice. So this is pretty important. Temperature varies with latitude. In the equator areas, they get the most direct sunlight and the most concentrated sunlight. However, as you move to the north and south poles, that amount of light gets spread out over a larger and larger area. So every beam, you can think of light as a whole bunch of thousands of beams of light moving in pretty much a straight line. And when they hit the top of the earth, they're spread out over a larger area of land, meaning that the areas at the top of the earth, the North Pole, and the South Pole at the bottom, receive per unit of area less light than at the equator. And that's why you have days and nights being 24 hours long in the northern and southern hemisphere, and the coldest temperatures as well. So reasons for the seasons, again, has to do with that 23.5 degree tilt and the rotation of the Earth around its axis and the orbit of the Earth around the Sun. Okay, this is what we're going to want to remember for lab today, is gravity, mass, and distance. And we covered this a little bit, or we covered this in detail in prior chapters. Gravity attracts all objects towards one another. We know that to be true all the way from super small particles like the quark, protons, neutrons, electrons, all the way up to planets and suns. If the mass increases, the force also increases. So the bigger the mass, the bigger the force. The other thing is, if distance increases, the force decreases. So the closer something is, the larger the force of gravity of one object acting on another. Okay? All right, let's keep that in mind for the lab that we're going to do today. Oops, don't want to open GarageBand.